Okay. So we'll start with, we have learned some parts of data reduction already, right? How to deal with noisy data, like just basic concepts about how to deal with noisy data, how to deal with outliers, how to deal with skewness. Okay, those parts we have already covered. So this will be about another method for data reduction, that is attribute subset selection, right? So let's start. So you can see it is also another name for this is feature selection, right? Another name for the attribute subset selection is feature selection, because why? You have you in your data set you will have a lot of features. You have a lot of features and it is a higher dimensional data set. Your job is to select the most important part of the features in your data set, not all of them, because it's already a high dimensional data set, right? So if you don't understand a higher dimensional object, what you do? I will give you a biology oriented example. Like when we fall down or something like that happens, a case happens. What happens? They suddenly check your brain scans, MRI, right? They check the MRI scans. Now your brain is a 3D object, is it? Brain is a 3D object. Do you can interpret that, right? So brain is a 3D object. So why we see a diagram of something like this, right? We see an MRI image like black and white image. Okay, so what is that? Your brain is already 3D, but you are seeing something like a section. So what we are basically trying to do is like you scan the whole of the brain, but in sections, So the 3D object of the brain, this is the brain, suppose this 3D object of the brain is being sliced into number of slices, and those slices, each of these slices are understood. Okay, what happens to each of these slices, right? So using each of these slices you can reconstruct the 3D version of the brain. Understanding, right? Okay, so therefore this, in order to understand the 3D part of the brain, you need to understand one of the slices, that is the 2D version of the brain. So you're reducing the dimension here. Instead of studying the whole 3D, you are taking a slice that is a 2D. So therefore, if you want to understand any higher dimensional object, always try to project it. Always try to project it, right? So you can see, like when we walk, we have a shadow. We have a shadow. What is the shadow? It is a projection. It's a projection. The light falls on us. It is a projection. So based on that, you can easily, without knowing me, without actually seeing me, you can just by seeing the shadow, you can always tell whether like all the features of the person, how much height it can be, is he fat or is he slim, okay, is like many parts of it. Okay, so I'm giving you just an example. So therefore, if you want to understand a higher dimensional object, your idea should be to lower the dimension in some way, so as to understand, because as human beings we are trained, our brain is trained to understand only 2 dimension or 3 dimensional objects, right? More, not more than that. Our brain is not yet conscious to understand dimensions beyond 3. However, they still exist. Okay. Anyway, so attribute subset selection. So it's a process in your data mining and machine learning techniques where you select a subset, as I told you, you select a subset of relevant features, also known as attributes, from the original data set to improve the performance of your model. Okay, so you have a bigger data set. Your job is to select only the chunks, important chunks from that. In that way, you are not only reducing the data set, like reducing the number of features you are taking, but also like it helps your algorithm run faster. Okay, so we will see how PCA also helps in this process. Anyway, so these are the steps in your attribute subset selection. So you first start, I mean, there are many methods. One is like forward, another is backward. Okay, and another one we might see is like some genetic algorithms also. However, we'll not go into details. We'll just touch on the surface so that you just get an idea of what these algorithms are, and like just a logic behind it. Anyway, so we'll see. So start with a full set of attributes. That is the original data set. Right? So your search strategy is like we have to explore all possible subsets of those attributes, because some of the subsets can be highly efficient. Okay, so given a data set, do you already know in prior which are important? No, you don't know it, right? So unless it is highly intuitive, we don't know. Okay, so therefore we have to put some trial and error methods for that. Okay, we'll see. So there are different methods you can see, like forward selection. So what is forward selection method? You start with none of the features but add one by one. Okay, carry with an empty basket, you go with an empty basket. Okay, and where your lot of features are there, okay, you put one of the features in your basket and test the performance. Is it giving a good performance? If not, reject that, take another one. Okay, if it is giving good performance, keep it. Okay, I hope that is kind of intuitive, right? Backward, we'll see each method detail. Backward elimination, different case, start with all of them. So take the bucket and all of the features are inside the bucket. Now you have to eliminate them. Like if you take out one of them, whether the accuracy is still maintained, no, accuracy is not still maintained, then keep it, try another one. Okay, like that. It's just like selecting your backward selection is like selecting best vegetables for your home, right? So what you do out of that basket, suppose you have lot of tomatoes you want to buy, like what you do, like you check the tomatoes, it is looking or good or not, and if it is not looking good, you put in the basket and take the one which is good, right? So fine. But what the shopkeeper does, the shopkeeper does something different. Shopkeeper does backward selection. So when he already has a basket full of tomatoes, in order to show the customers that the tomatoes are of highest quality, what he will do, he will try to, as a hope of good heart person, we hope that he will remove the bad tomatoes, right? So he'll be removing the bad tomatoes and keeping only the good tomatoes. Okay, so you can see how as a customer we are using forward subset selection and how the shopkeeper is using backward subset selection. Okay, anyway, another is exhaustive search. Exhaustive search means try all possible subsets, try all possible subsets. Okay, all possible combinations we should try, and which one is giving you highest accuracy, right? Another is heuristic or randomized search involving genetic algorithms or simulated annealing, but we'll not discuss those things much in detail. Okay, we'll see. So, but how we will know that this subset is good? How we will know? What is the test criteria? What is the test criteria? Like for you to come to a university, you have to give some nationwide test, right? So if you pass through the nationwide test, you are eligible to come to the university to attend the classes, right? So therefore, there is a tolerance criteria in your marks in your entrance exam, right? So similarly, if you consider more than this mark, you are eligible to come to the university. So similarly, which subset is good? They have a test criteria for this. This is known as significance level. Okay, so significance level, p-test, hypothesis testing. Okay, so there are a lot of statistical analysis where you can find out whether a subset is representing lot of qualities in my data set or not. Okay, so something like you will see that chi-square test also there. So you see evaluation criterion, like measure the goodness of a subset. Which subset is good or which subset is better? Okay, so there should be a statistical test behind that. There are many filter methods like correlation you can use, mutual information, entropy. So those are some of the Shannon entropy. Those are some of the statistical tools we you can use, like to know which subset is better for your algorithm. Okay, chi-square test also. So, some methods here to evaluate your subset. Wrapper methods like use an ML model, like use a machine learning model to do that. Evaluate subsets by training and testing the accuracy. Okay, you can also use a machine learning tool for that. Embedded methods already built into the model, right? So these are like something like lasso regression, which you will be covering in the next semester. Okay, lasso regression, different kinds of regression, lasso regression, logistic regressions, all these things. Okay, so what is the benefit of this attribute subset selection? First of all, and most important one, reduces the dimensionality. Okay, you have a bigger data set, only you are selecting the most important parts of the most important features from the big data set. So it reduces dimensionality because you are eliminating those which are not important. right? You're eliminating those features which are not important in your dataset, right? And only taking the most important ones which give you highest accuracy, right? In that way, you are reducing the dimensionality of your dataset. So therefore, it is useful in data reduction. Reduces dimensionality. It improves the model generalization. I hope this might not be understood by many of you, but it's like of a machine learning like language for this. Okay, what is model generalization? We'll skip this. Okay, decreases training and testing time, of course, because if you have a lot of features in your data set and you are using suppose wrapper methods which uses a machine learning model, then of course the testing and training time it spends on each of the other features will be reduced, right? So therefore in that way it reduces and makes your machine learning algorithm run faster, able to classify prediction and classification can be done more efficiently, right? Enhances interpretability. You will get to know what we mean by this like with an example. Okay, so let us see with an example, like suppose you are predicting house prices. Is this visible, right? Visible. So so it's like it's let us see this example, like why it's not working. So let us see with some example, like you are predicting house prices with attributes. Okay, what are the attributes of the data set? You have these features or attributes in your data set. That is, what is the size of the house? Like what is the square feet of the house? So whenever you want to purchase any house or something like that, they always ask you, right? How much is square feet or how much is the full area of the house, right? So what is the number of bedrooms in that house? What is the number of bathrooms in the house? And zip code. So where the house is actually located. Is it located in a very outside of the city, outskirts, or is it located in a like a mall area or where you have all access to the required things in your household, right? Owner's name, who is the owner, okay, and paint color, okay, so what house what color of the house is painted with, right? But you can see which one is the most important ones, right? So you can see like house owner name and paint color might not be important, okay, because the person can always once he takes over the house can always paint and renovate it, so therefore it is not kind of that important. Owner's name is also not that important, okay, because whoever is the owner, finally the house will be your name, right? So most important features are these. So actually these features are not that important, okay. So therefore if you include these in your data set, it just increases your dimension of your data set, right? So better to remove them, right? But this is a very intuitive example through which you can understand whether this data set should be, this feature should be removed or not, right? But if there are a lot of data set like features where it is not intuitive, we'll see with a PCA example today, like there will be 30 features about the breast cancer, okay. So 30 features will be there and you will be selecting around 2 to 3 features only, most important ones, okay. So other features will not be that much giving you highest amount of accuracy or something like that, but they are important, okay. Okay, so here you can see attributes or features like owner's name and paint color might not be useful, so subset selection would keep only the relevant features, that is size, bedrooms, bathrooms, zip code for better prediction, okay. Fine. So let us begin. So with a forward selection method, right? So this is known as stepwise selection. So it's a greedy search strategy. So what we mean by greedy search strategy? This we will cover in upcoming slides. Okay, what do you mean by a greedy algorithm or greedy search algorithm? Okay. For subset selection, so you start with no attributes, empty model. Okay, you start with nothing, then add one attribute at a time. Start adding one attribute at a time. At each step, try adding each remaining attribute individually to the model and evaluate the model performance. Like how you can evaluate the model performance if you're using any wrapper method using machine learning tools, you can use the ML accuracy model, the training and testing accuracy of your ML models, right? So that is accuracy. R2. R2 also you can use if you are using lasso regression models or different logistic regressions. Okay, R2. Okay, I hope you might be knowing about R2. If you're not knowing about R2, there is no issue because you will be learning in the next semesters. Okay, in variety of courses. So error rate and AIC and BIC method. I suggest that at least try to Google and get to know these methods. What is AIC? What is BIC methods? Okay, just to know that these methods are there. I mean, okay. Choose the best attribute. So after evaluating the model performance, you will get to know if after adding that attribute, whether I get good amount of accuracy or not, right? If I get good amount of accuracy, better to keep it. If I don't get good amount of accuracy, eliminate it, right? Simple. So choose the best attribute, the one that improves the performance the most, okay? And repeat this process until adding more and more attributes doesn't significantly improve performance. Suppose the model performance you got is around 87%, and again you are adding another attribute, okay, and you are getting something like 87.2. So that adding of that attribute doesn't make much changes in your accuracy. So therefore, no need to, you might not be interested to add to the model. Okay. So in that way, we have to look. Okay. Okay. So let us see, like suppose this is an example, you are predicting exam scores with 5 attributes. So these are your 5 attributes. So suppose like a person, how much he scores. Suppose he got a score of like say 89 out of 100, right? Now how he got 89 depends on many factors, like how much he has invested into the hours of study. Okay, the more time you invest is one of the factor, but not all the factor. It means that you can just turn the book on, but your mind will be something else. So it doesn't really matter. What matters is also how many times or what is your attendance rate in the class. Okay. Of course, your IQ level, favorite color, birth month. So birth month doesn't decide how much well you will score in your subject, right? And also your favorite color doesn't decide how much marks you will get. So therefore, you can easily see that only 3 features are important here. Okay, only the first 3 features are most important. Other 2 are not that important. So how we will start with forward selection? Start with nothing. Okay, good. So then what I suggest is test each attribute separately. So with only hours of study, you only took singleton set, that is hours of study, and you found that your accuracy has been 80%. Okay, your accuracy is around 80%. Then what you do? Okay, fine. Then you turn to attendance rate. Okay, accuracy is 65%. Good. But you see that attendance rate has given you less accuracy as compared to your hours of study, right? Let's go to IQ level. IQ level is also giving you 60%. So others perform poorly. So what you should choose out of them? This one. Okay, hours of study. So out of these 3 data sets, these 3 features, you found out that yes, if I chose hours of study from my features, it will render me highest amount of accuracy, right? So that will be in your data set now. Now, what is your next job? Next job is finding another feature. Your next job is finding another feature right now. So you will see that now the step 3 is add the next best attribute. Add the next best attribute. So what attribute we have chosen so far? Hours of study, right? So now what you do, now add attendance rate to it. You found that yes, by adding attendance rate to hours of study, you got the accuracy of 87%, right? So now what you do, now if you include IQ level, your accuracy is around 82%. Yes. So what you should choose? The highest amount of accuracy. So you can choose the model of hours of study and attendance rate because it gave you around 87% of accuracy, right? So you carefully saw how we are selecting a subset of the data set which gives us highest amount of accuracy, right? Without taking all of them, still you are getting around 87% of accuracy. So choose attendance rate, continue until no further improvement is there in your accuracy, right? So final selected data set or subset is hours of study, attendance rate, but it's up to you. You might want to go beyond it. Like the other one was what feature was there? Is it IQ level? Yes. If you're adding IQ level, you can check whether it improves the percentage or not. If it doesn't improve, you might not keep it. If it significantly improves, like 93, 95, then of course it should be kept. Okay. Then what you will understand is this is step 5. After like that is step 6 is you will again choose favorite color, suppose. So if you choose favorite color, what will happen? Your accuracy might not change. We already know that, right? So then you will eliminate that. Then after that you choose the remaining one, that is birth month. Again, it is not increasing your accuracy that much. So don't take it. So finally you will be left with 3. Okay, so you can easily test that. Okay, so let us see, like the pros in this are like it is simple and intuitive, computationally a bit faster than exhaustive search. Of course, it's not that computationally faster because you have to test at each step, right? So so this is like if you want to implement this in your coding algorithms and all, you have to use a for loop. Okay, for loop, and what you do is like at each of the for loop you check accuracy, check accuracy at each step. So therefore, this is known as a greedy algorithm because you are testing the accuracy at each step. Such kind of algorithms where you test something at each step for each element is known as greedy. Okay, so we'll see that. Okay, so this is a greedy algorithm. The cons of this, because once an attribute is included, it cannot be removed. Okay, even if it becomes redundant later. Okay, once you put that, I mean, you cannot discard it. Okay, because that is what is a greedy algorithm is about. Of course, when this is just a tiny data set for your example and with very simple intuitive examples, but what will you do if your data set is pretty large? Okay, so then of course it will be computationally demanding. Okay, because it is already a greedy algorithm. So the most higher amount of features you have, larger data sets entries, it might fail. Okay, not fail, it might be computationally expensive. Okay. So this is, let's again come back to backward elimination. So it is same thing like, but this is stepwise elimination. So remind yourself that this is forward selection was stepwise selection. Forward selection was stepwise selection, whereas backward elimination is stepwise elimination, right? I hope you can understand the difference between the two. Right? So it's another feature selection strategy where you begin with all of them, begin with all the available features. Okay, you begin with all the available features and then remove one by one until the most important one remains. Okay, it's just like the shopkeeper example I gave you. Okay, when the shopkeeper buys tomatoes, he doesn't have an opportunity to check that 10 kg of tomatoes at that time because it will be covered. So when he brings it to his house, he knows there will be some loss, and he starts to eliminate the bad tomatoes from them. Right? Okay. Start with all the features included, and again at each step. So this is also a greedy algorithm. This backward is also a greedy algorithm because you are evaluating the accuracy at each step. You are evaluating the performance model at each step, right? Using criterion like p-value in regression, error increase, or R2, or any ML model if you are using. Okay, or maybe this is also important, that is significance level. So usually what happens is if your significance level of your feature is more than 15%, then you eliminate that data. You eliminate that feature. So that's one of the criteria, significance level. P value R2. So you see, when you will be learning about regression, you can connect to this. When you will be learning about regression, you will be given an exercise to find the value of R2. Okay, what is R2? Okay, so there is a very nice algorithm to compute R2. Basically, what you do is residual. Like if you have a data set like this, okay, and what you do is just predicting the regression line here. Okay, predicting the regression line here. Then these are your residuals. The distance between these two, right? These are your residuals. Okay, these are your residuals. So using these residuals, you compute the coefficient of determination, that is R2, right? So that's the idea. Okay. So what the idea is, like, remove the least significant attribute. Okay, one that contributes the least to model performance. You remove it and retrain the model again with remaining attributes and repeat this process till you see a big drop in performance. I mean, if you remove an important, suppose like if you have a bigger data set and you removed one of them, before removing your accuracy was around 92%. Yes. So if you remove that feature from your data set, what happens? Suppose your accuracy reduced to 80. Then you know that this feature is one of the most important one, because as I removed this feature, it dropped accuracy to 80%, right? So therefore, I should not eliminate this feature. Rather, I should keep this feature, right? So you can get that intuitive idea. Is it getting the idea, right? Hmm? Okay, so we'll see again with an example. Suppose you are predicting diabetes risk with attributes. Okay, so what are the attributes here for features like age? Because sometimes people, it doesn't matter actually much, but people with uh, lower age also are getting the diabetes risk. Okay, blood pressure, BMI, smoking habit, and eye color. Which of them contributes a lot to your diabetes risk, okay, factor? Okay, we'll start with all five. For your I mean backwards elimination method, you start with all five. Train the model using ML tools or any other algorithms. Okay, so find the least significant attribute. Of course, the eye color doesn't matter because it may be brown, it may be pink, yes, it may be green. Okay, so yes, so that is least attribute. People still get diabetes risk, right? So therefore, eye color has a negligible effect. So therefore, it is desirable to eliminate that. So remove eye color. If you remove eye color, now what happens? What you are left with? The other features, that is age, blood pressure, BMI, smoking habits, right? Suppose now smoking habit does have a little contribution, you eliminate that. Now you are left with these three, right? Okay. So I did not type the accuracies here. It could have been better. I mean, if you removed eye color, suppose, let me start again. Suppose with this set of attributes, your performance was around 90%. Accuracy was around 90%, right? Now, let us come to step two, okay, where you removed eye color. By removing eye color, your accuracy dropped down maybe to 89.5 or something. Then it is not that much, uh, I mean, difference, right? It is just 0.5, right? So you can remove it. And if you remove smoking habit, it might reduce to 89.2. Yes, so it has negligible effect. It has negligible effect. Even after removing these two features, previously you were having 90% accuracy, but even after removing these two features, your accuracy turned out to be 89.2. So therefore, you can see that these two features doesn't actually contribute much to our models, right? So therefore, you can eliminate them. Therefore, you can eliminate them. And you're left with these three. But suppose in step six, your accuracy was 89.2, and you again do the backward elimination part, that is, you remove blood pressure. You remove blood pressure. Then you will see accuracy suddenly drops down to 50, because blood pressure is one of the most important criteria diabetes risk, right? So therefore, if you drop the blood pressure feature, you will see accuracy drastically reduces. So this is what you will come to know, that yes, blood pressure is an important feature, because it drastically reduced my accuracy by 30%, right? So same set of pros and cons it has, like um, so this is one of the most important one. This is one of the most important point here. So backward selection method, it considers all features from the start, and it is kind of better than forward selection if many of your features are correlated, right? Suppose now many of your features in your data set are correlated, then your backward elimination is important rather than forward selection. Why? Now the amount of ideas you got, now the situation I am asking you is, suppose in your data set you have a lot of features. That's where data direction you will use for this, right? Backward elimination, forward selection. Now I'm telling, suppose your number of features, some amount of features in your data set are highly correlated. That means, you understood, right? The correlation means one is like correlated with other, right? Some features can be like that. Now if some features are like that, then which method will be better? Is it forward selection or backward elimination? Backward elimination is better. Yeah, that is what is written in the slide. But why? So this is for you to mind boggle a bit. Okay. So this is important. Okay, this is important. Like, you can be asked. Hmm. Then hmm. 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 Yeah, I think very close to the answer. Both of them very close to the answer. But you have to frame it better a bit. You have to frame it a bit better. So you need to understand why backward elimination is working good when you have highly correlated features. Okay, of course there will be a lot of features which are correlated, right? Maybe you can say BMI and height. Suppose in your previous feature, suppose you put height and weight. These are two extra features I put in my dataset. But you already know that BMI already is correlated with height and it is already correlated with weight, isn't it? We saw that in last class, right? This is data transformation. Hmm. Data transformation, no, BMI. Oh, good. Okay. So I don't remember where I kept that slide. Yes. So body mass index formula, let us revisit. Okay, you can see BMI depends on weight and height. It directly depends on weight, directly proportional to weight. The people with more weight will have higher amount of BMI, and the people with higher height might be having lower BMI. Yes. So you can see BMI is weight by height squared, right? So you can see this that it is kind of correlated with weight and height. So now suppose, so you can see, let us go back to our slide. Yes. Now, if we include height and weight, then BMI is correlated with these two features. So now what you do is an example like this can come in your exam. Like suppose you have this example, right? What you need to do is like maybe this example will be given with height and weight and will be asked like if you take forward and if you take forward selection and backward elimination, right? If you take both these methods, which one can perform better? Okay, so your idea will be like since these features are correlated, you can easily see that yes, if your features are correlated, backward elimination works better than the forward selection method. Okay? And you have to give an intuition also why that is the case. So in exam, you can get some examples like given an example, you will be asked to do something. Okay, that will be some kind of your final exam questions towards December you will have. Okay. So yeah. So again, it is computationally expensive than forward selection because you start with a larger model. Okay. So even though it is computationally expensive, but it can give you higher amount of accuracy in your models if you have highly correlated features. Okay. So therefore, it has a pros and cons. Again, it is a greedy algorithm. Once a feature is removed, cannot be added back. Once you remove, cannot be added back. So let us see what I have been talking about greediness. Okay. So what is greedy? Both forward and forward selection and backward elimination are greedy algorithms. So what do you mean by greedy in algorithms? So an algorithm is called greedy if at each step it makes a locally optimal choice. Because I hope you are able to make a correlation, right? In both of these methods, because in forward selection what you were doing, you were selecting one of the methods and you were checking whether that did I do a locally optimal choice, whether my choice was good or not. How? I took an accuracy like ML model accuracy or R2 value, whether I am getting good amount of accuracy or not, right? So did I make a good locally optimal choice, and I'm checking that at each of my step, right? Without looking ahead, means I took one of the feature without giving attention that there can be other features also. Which features to choose, I don't know. I just took one of the features. Okay, maybe there is one feature remaining which has highest amount of accuracy, and I did not pick it first, right? So without looking ahead at the global best solution. Okay, so what greedy algorithm does, you are locally optimizing, not globally optimizing. Okay, you are looking what is best for you now. You are not looking what is best for you over the years to come. That's what is meant by that. Okay, so if you, I will tell my example. So I like noodles. Okay, so I eat noodles, but rarely. Okay, but eating noodles is not good because it's a highly ultra processed food, right? But by eating noodles, I am satisfying myself at that time for that day locally. But over the long run, it might affect me, right? Over the long run, it might affect me. So I'm not making that much of a globally optimal solution, but I am making a locally optimal solution choice. Okay. So I hope that example kind of relatable. Okay, means you know that it is bad, but still you do at that moment. Okay, so it doesn't plan ahead. That's the idea. It doesn't plan ahead. So this is one of the catchy terms. Greedy algorithms doesn't plan ahead. Okay, it just picks the best option right now for you in your algorithm. Okay, so this is the greedy nature of forward selection. Suppose at each step it asks which single feature improves the model the most. If I add it right now, okay, if I add this feature right now, which gives me highest amount of accuracy, without knowing that there can be another feature which has or which can give me more the accuracy than that. Okay, then it locks that choice, and never revisits it, okay. So by mistake you took that feature, now it is in your box. Now we know once you took the feature you cannot eliminate it. In backward elimination, once you eliminate it you cannot put it back. So that there is a very nice difference between these two algorithms. In forward selection, if you took someone in, you cannot eliminate them, right? Like if some student enters the university, can you eliminate them? Unless they do something very drastic, you don't eliminate them, right? So therefore, that is forward selection. Backward elimination is example. If you if you are left from that university, can you come in back? I mean, after some years, you of course can try, but you cannot come in back after some time or months or something like that. Once you are gone, you're gone, right? Okay, so that's how these methods are there. Another is exhaustive search. That means without any logic. Without any logic, consider all possible combinations. All possible combinations. So exhaustive search is the brute force method of attribute subset selection. It tries all possible combinations. It tries all possible combinations. Okay, of attributes and select the subset that gives the best model performance according to some evaluation criteria, that is accuracy, error rate, R2 value, or PP value, or significance level is like greater than 15% or not. Okay, so these are some of the tools you can use. So all possible attributes. So given a subset of n, like maybe you have n number of elements in your data set, then how many possible subsets it can have? Try to check. Try to check whether this is correct or not. Don't believe me. Try to check by example. Try to check using 3 different elements in your data set and try to see how many possible data sets it can have. Okay. Might be wrong. I might be wrong. So anyway. So I'm just trying to give you an idea why I consider the size here, because if your size increases, if your data set increases, suppose your data set increases, then like let us take an example from this class. You are 100 in numbers. Yeah, you are 100 students in numbers, right? My choice is like I will select 2 of you, but which 2 of you I don't know. Which 2 of you I don't know. So what choice I have? I can choose how many combinations can it have. How many combinations can it have? Permutations, combinations. Okay, so you need to know these things. Is it 100 C2? 100 C2. You select 2 out of 100. 100 C2. I hope you know P, NPR. No. Again repeated. Okay, anyway. So, okay. For each of your subset, train the model again, evaluate the score, select the subset with best score. But it is not, it is highly computationally expensive. Okay. We'll see with an example. Suppose you have 3 features, x1, x2, x3, like what are the possible subsets of this excluding the empty set? Excluding the empty set. Excluding the empty set, what other features you have? Like you can see the singleton sets, x1, x2, x3, then elements with two elements in the subset, x1, x2, x1, x3, x2, x3. Then the set itself, x1, x2, x3. Okay. So you can see like you can see how many 1, 2, 3, 4, 5, 6, 7, and another is empty. Okay, totally makes 8. 2 to the power 3 minus 1. Okay, 2 to the power 3 minus 1. So here you have actually 2 to the power n subsets. When you eliminate the empty set, it's 2 to the power n minus 1. Okay. Okay. So if your modal accuracy, now what you do, what this for exhaustive search does, you have x1, x2, x3. Now it doesn't care. It doesn't care like at each step which one is best, which one is bad. Doesn't care all that. You take all possible combinations, and in all possible combinations you find the accuracy. Okay, like you find the accuracy for this one, this all the 2 to the power n minus 1 data sets, like subsets, right? So if you do that and you find out, suppose that your x1, x2 gives highest accuracy, then you choose x1, x2. No logic is used in this algorithm. What other possible subsets are there? Choose all of them, find accuracy of all of them, choose the best one. Okay. Fine. So these are all the examples so far in your attribute subset selection, which I wanted to cover. So you got a basic idea, is it? You got a basic idea of how this method works, right? Isn't it? Any issues? So what we learned is like how now you can see how this can be used in data reduction. Note that maybe if you take all these subsets, like maybe let us take the BMI example or the diabetes risk. So this example, maybe with the remaining set, the total set of data you have or features you have, maybe your accuracy is 95%. Okay, your accuracy may be 95%. It might not be 100%. Okay, because you still lack with a lot of data. You never get all data sets to reach to 100% accuracy. Okay, so suppose you are 95% accurate. Okay, then you remove some of the parts, then of course your accuracy will drop. That's the price you pay for data reduction. You cannot have data reduction with the same amount of accuracy. I mean, there will be some loss, of course. Okay, there will be some loss in your methods. Okay, so maybe if you use forward elimination, maybe it can drop to 92 or maybe 93, something like that. But it will drop. You cannot have same 95%. Okay. So that's the price you pay when you are doing data reduction, because you are already removing chunks from the main thing, right? I hope you get that. Okay. So what shall we do? Hmm? Okay. So next we should start with PCA, Principal Component Analysis. And I want we to start with a fresh mind. Okay. So let me talk.